Okay, so this is the final video for content for the week 2 of the post-Easter work for Reigate Maths. This is looking at, as a lot of this new specification does, modelling using the topic we've just been looking at. So this is modelling using sequences and series. So often, and in most cases, because of the way population growth happens, or decay happens, or depreciation of value of things happens, a lot of the formulae and the situations we're going to look at are modelled with a geometric sequence or series. But you do have to be careful. A geometric sequence is used for working out how much you put in, say, you get with compound interest every year. Okay, not the total amount that you have, but the amount of stuff that you get in a particular year. Whereas a series, so this is in an individual year, for example. A series is for the total earned or saved, or something like that, for example. So the thing with this is just carefully read the question and take into account what it's actually asking. So let's have a look at the question on page 9 of your workbook. Okay, so Josh invests £1,200 in a bank at a rate of interest of 2% per year. Produce an expression to determine the amount of money he has in the bank after n years. Okay, so this is not the total amount that he has been putting in. Okay, or it's not. So if you think about it, in the first year he has 1,200. So the other thing with sequences and series with modelling, quite often the initial value will be given, instead of A1 or U1 like we've been doing, it's given A0. In the second, so after 1 year, he's got 1,200 times 1.02, so an increase of 2%. Oops, 0.02 to the n. Notice this is the amount of money that he has. We're not adding them together. He's not putting in. So he's not starting on 1,200. That's how much he puts in first. He then puts in this amount. Then he puts in this amount. If it was that, then we'd be adding them together. But that's 2. Okay. So we can see that this is a geometric sequence. However, notice the difference. So normally, for a geometric series sequence, we have that. But notice how things change for the after the year. So this is after 1 year. We can see this number is 1. So this will be after 2 years. We can see the number is 2, and we can also see here that the power matches. So this formula doesn't really work. So this is what I said in the previous video with, if you're not sure, write out some terms and see what happens. Write out things like I've done here in green as well, if you need to. You know, there's nothing wrong with writing some working out and annotating it. Okay, just so you get that, oh look, after n years, the amount he has is 1,200 times 1.02 to the n, not the n minus 1. So you do have to be very, very careful with these. Okay? Because although, yes, for a sequence, we could do an nth term formula using this, it wouldn't be correct here. Because the initial, we use a 0. Okay, we don't use a 1. So, B. I'm going to need a new page. After how many years must he wait to have increased his initial investment by at least 25%? So, increase by 25%. So let's have a think about this. If it has increased by 25%, he needs to have an amount of money equal to his initial investment times an increase of 25%. Okay, which gives us 1,500. So that's how much we are looking for UN to be. Once you realize that, well, the question says at least 25%. So we actually want UN to be greater than or equal to that. Once you've got that idea, it's just a case of doing very similar questions to what we've done before. We know that from part A, the UN is 1,200 times 1.02 to the n. And then this is just a logs question. Uh, 1.2. Yeah. Oh, sorry, 1.25. Okay, so we know that log 1.02 to the n is greater than or equal to log 1.25. Again, remember to being careful with using logs because it's an inequality. Do the long way around. It works every time as opposed to just some of the time. Because we know that log of 1 point something is positive, so we don't have to worry about this. So n is greater than or equal to, you can use any log, doesn't matter. So I'm just going to use ln because it's here. 1.25 divided by log 1.02. And we get that we get the answer as 11.27 years. So in order for this to the amount of money he has in his account to have increased by at least 25%, if n is 11.27 years, that is exactly when it hits 25% extra. Okay, so Josh has to wait 12 years, because in this case it is in the 12th year where this happens. So remember, the first year goes from 0 to 1, So the 11th year, so the 12th year goes from 11 to 12. So he has to wait 12 until the end of the 12th year. Because at the start of the 11th year, sorry, the end of the 11th year, the start of the 12th year, he doesn't have 25% extra. Okay, so before I set some questions from the textbook, I want to do one more example, which is an interesting one that sort of makes you think. So a piece of paper, oops. So we'll say A4 paper is folded in half repeatedly. Okay, so we take it, we fold it in half, we fold it in half again, fold it in half again, and so on. Okay, if you want to try this, take a piece of A4 paper and try and fold it in half, then in half, then in half, and see how many times you can get. You should find it's not many. So the thickness of the paper is 0.5 millimeters. Okay, so not very thick. So we want to, part A, work out the thickness of the paper after 4 folds. So again, if we're careful with our notation, we can really make the question easy for ourselves. So after 0 folds, the thickness is 0.5. After 1 fold, we have doubled the thickness. So after 2 folds, we've doubled the thickness twice. So after 4 folds, we've doubled the thickness 4 times, which is 8 millimeters. Now, just think about a piece of paper. 8 millimeters doesn't sound like a lot, but it's a little less than a centimeter. Okay? That's quite thick. So let's look now at part B. Find the thickness of the paper after 20 folds. Okay, so we know the nth term formula already. So we know that U20 is going to be 0.5 times 2 to the 20. Okay, so 0.5, that's, yeah. Okay, which if we do on our calculator, we get 524,288 millimeters. Let's just think about that. Because part C is state one reason why this may not be or might not be a realistic model. Let's think about 524,288 millimeters. So millimeters to set to meters, we divide by 1,000. Which gives us 500 meters. Just say that again, 500 meters. You've taken a piece of A4 paper, which is a little bit bigger than it's not quite, it's a bit less than double my sheet of my pad of paper here. I'm working on B5, I think. But, you know, it's effectively that. Double, more or less double that. Try folding, take a sheet of A4 paper and try and fold it 20 times. You'll find you can't do that. If you could, your piece of paper would be, your little folded bit of nonsense would be 500 meters thick. Okay. However, just talking about that is not sufficient to answer this question. Okay, what we need is a reason why the model might not be realistic, not talking about necessarily this number we've calculated. This is useful to show us that the model's nonsense, or the model is only valid up to a certain point. Now, some of you may know, just because you do, if you take a sheet of paper, actually sheet of paper any size, and fold it in half, then in half, then in half, and so on, the maximum number of times you can do that is 7. Okay, so it is impossible to fold a sheet of paper this many times. So the model is unrealistic. Okay, if you don't believe me about the sheet of paper, try and take a sheet of paper, regardless of how big it is, and try and fold it more than 7 times. You'll find you can't. Okay, without it ripping, or without doing anything to it. Obviously, if you do things like dunk it in water, you can fold it more. But if you just take a sheet of paper and fold it, if you need that to convince yourself that what I'm saying is true, then so be it. Once you've done that, come back and have an answer of the following questions from exercise 3I, which is on pages 84 to 86 of the textbook. Okay, so I might do question 1 and 2, then questions 7 to 9. Okay. For those of you who want a challenge, have a go at questions 14 to 16 as well. Okay, and that's it for week 2. In terms of the content, next week we will be looking at going away from sequences as a series and looking at a different unit for measuring angles. Thank you for watching.